Okay, so next speaker for today is Professor Vasyl Ostrovskyi from Institute of Mathematics, Ukraine National Academy of Science. And the title of his talk is on representation of Qij commuting isometries. So you are welcome.
Thank you. Can you hear me?
Yeah.
Yes. Okay. Okay. Good morning to everybody. First of all, I would like to thank the organizer for the possibility to present my talk on this event. And as you see, the title of my talk is on the presentations of Qij commuting isometry. This is a talk based on joint research with Olga Ostrovskyi, Daniil Proskurin, and Yuris Samoilenko. So what is this all about? Oops. Something's, sorry. Oops. First of all, what is Kunz and Kunz-Chaplet algebras? First of all, I would like to say what is Kunz algebra. This is one of basic notions for this talk. And Kunz-Chaplet algebra is a C-star algebra which generated by the following elements. You have generators which satisfy such relation. If you speak about representation of Kunz-Chaplet algebra, you have some Hilbert space, and you have operators. You see that for if J and K are the same, this is identity, so this is isometries. And this relation means that these isometries are with orthogonal ranges. So geometrically, you can imagine Kunz algebra as follows. You have a Hilbert space, some Hilbert space H. You have, this is the same space, but I painted it twice. So this is again the space H. So if you have some infinite dimensional subspace here, you know that all separable Hilbert spaces are isomorphic. So there is an isometry which maps the whole space to this subspace. And also if you have other subspace here, you can consider the isometry which maps to this other subspace, and so on. If you have a number of, if you have a Hilbert space which is decomposed in an orthogonal sum of its infinite dimensional subspace, then you can consider isometry which identify the whole space with its subspaces, and this set of isometries is a Kunz algebra. In general, this is Kunz-Chaplet algebra, and if these subspaces cover the whole space H, this is Kunz algebra. So in general, this isometry may not necessarily cover the whole space. So we get a Kunz-Chaplet algebra. So this is Kunz-Chaplet algebra. This is exactly a family of projections in a Hilbert space with orthogonal ranges. So this is a very natural object, algebraic object, and moreover, this algebra is interesting because this algebra is an example of so-called algebra with weak ordering. And I will speak what is algebra with weak ordering. This is a star algebra generated by the following set of elements. You have again some generators. You have the formal adjoint, and the relations are like this, but with additional terms. What these terms mean? These terms mean that this is quadratic algebra. This is second order relations, and this means that all starred generators can be shifted to the right. if you have some word of these letters, you always decompose it into a sum of into linear combination of words where all S without start will be left side, and all started letters will be right side. So if you have this family of coefficients, you can construct some in natural way an operator in the tensor product of and the tensor square of the dimensional space, and there is a conjecture which was stated by Jorgensen, Schmidt, and Werner, that if the norm of this operator is strictly less than 1, then this algebra has enveloping C-star algebra, and this enveloping C-star algebra is isomorphic to Kunst-Joplitz algebra. I would like to say that if there is equality, if the norm is less or equal to 1, or if norm is equal to 1, then this set of relations contains algebras like canonical commutative relations, which have no bounded representations, canonical anti-commutations relations, kinds of Kuon relations which arise in physical models, some quantum algebras. So these relations form a rather interesting class and rather wide class. And it is actively studied in different papers. But the conjecture is that if the norm of this operator is strictly less than 1, then the conjecture is that the following algebra, when you take a C-star algebra completion, you will have algebra which is isomorphic to OD. To Kunst-Joplitz algebra. This fact was proved for operators which have norm which is so this is approximately like this, but the conjecture is that there must be 1. There must be 1. So there is unknown area here. So okay. Next thing which I would like to say is Fock representation of this algebra. If you have algebra with weak ordering, for each algebra with weak ordering, you can define so-called Fock representation. Fock representation name is taken from physics cases where you have canonical commutational relations. For them, there is Fock representation. This notion can be extended to the case of any algebra with weak ordering. So Fock representation is defined the following way. It is generated by a cyclic vacuum vector, which is omega. Vacuum vector is again a physical term. And the condition is like this. This condition in physical models, this means that all operators SJs, all annihilation operators kill this vacuum vector, R0 and this vacuum vector. So Given relations in this algebra, one can see, because you can always rearrange in any word, you can rearrange letters in such a way that all stars will be to right, and maybe some elements which do not contain Sj at all. So you can, this relation shows that this condition determines the Fock representations uniquely. There is only one such representations, and the space in which this operator acts is generated by a vector of the following form. So each element of this family is corresponds to some multi-index finite of any length. Also it is known fact that, well, but you can write this formula, but in general case, it is not obvious that these representations is a star representations. But there is a statement, there is a result that if norm is less or equal or than 1, and if operator T is braided operators means the following braid relation, where T1 and T2 are constructor from the same operator T, but with the following condition. You have tensor product of 3 copies of CD. T may may act either here or maybe act here. So you can consider T with respect to this these two dimensions and identity with respect to this dimension. You can consider T2, which is T on this 2 dimension, and identity on this dimension. So if this operator satisfies these relations, which is called braid relation, I should note that this is braided relation are very common in such business. So if you have braided operator T, and if you have, if you know that its norm is less or equal to 1, this is also includes almost all interesting examples. Then in this space, which is generated by these vectors, there exists a positive scalar product in which this representation is in fact a star representation. If you take a star adjoint generator, you will have a joint operator. So in general, this is not true. So this is a fact of which should be discussed. It should be investigated. It should be proved that there exists a positive Fock scalar product for this particular Fock representation. So if you consider a general class of such letters with such relations, for example, some operators in some Hilbert space, you see that if this operator have some natural properties, these relations have a natural realization, can be realized by in Fock. But the question is this unique? This answer is no. This is unique, for example, for canonical commutation relations and maybe some other, but even in the case we are interested in the case where norm is strictly less than 1. So it almost definitely that this representation is not unique. We consider a particular case of these relations. We do not consider a general operator T. We consider a very particular class of C-star algebra. We denote this by WD, In fact, this WD depends also on some coefficients, but for brevity, I will just write WD. So this algebra is generated by, again, by the same elements. These elements are isometries. These elements are isometries, but their ranges are not orthogonal as in Kunst-Joplitz algebra, but satisfy such relations as J is 1 is equal to Qij multiplied by the same generators, but in inverse order. And we assume always this relation. This is automatically for consistency, so I will not stress on this. But what is essential, we consider this. So we probably assume that this algebra should be, could be, and should be isomorphic to the Kunst-Joplitz algebra, but we don't know it in general setting. Here. So if all these Qij are equal to 0, of course, we have Kunst-Joplitz algebra. Then we have zeros here, so we have Kunst-Joplitz algebra. But for small q, it is a conjecture that this is again this algebra, but up to isomorphism. So this answer that these algebras are isomorphic is known in the case only in the case D is equal to. If D is equal to, so if you have two isometries in a Hilbert space, with Q is strictly less than 0. So the corresponding sister algebra is isomorphic to the case where Q is equal to 0. You can explicitly write down other generators, which are some series in terms of these operators. That series converge in the sister algebra. So this is isomorphism, but not as algebra, but as sister algebra. You need to have an isomorphism. You should write some series and prove their convergence. So while it is known that the representation of Kunst-Joplitz algebras are well known, for this case, only Fock representation is known. So it's interesting to study some other representations, and maybe this will help us to prove that there is isomorphism in general situation. So we need some notations. We consider, we will work with multi-indices. So if you have a multi-index, we consider lambda m set of all multi-indices of a length n, lambda 0 set of all finite multi-indices of any length, and lambda is a set of all infinite multi-indices, infinite. So for each finite or infinite multi-index, we can write for finite multi-index, we can consider S alpha as a product of the corresponding generators. Also, we use a standard notation. If you have some multi-index, you can consider sigma alpha. This means that we just killed first elements. So we have an index of multi-index of smaller lengths, or we can add. Sorry, there is misprint. There must be alpha 1. Alpha 1, alpha 2, and so on. So we have a longer multi-index. So also, obviously, this can be extended to the case of all multi-index of any length. And also, we will define some constant which are depend on multi-indices. If we have j and I, we have only Qij. If you have some multi-indices, We define them as the corresponding products, which arise when we have commutation relations, and we can define this. We can define them also also for any multi-indices of finite length and infinite length. So this is some constant which arises when we try to reduce element of such form. If you have element of such form, then we have some constant, and then we have some other multi-index here.
Excuse me, please. How many minutes you need? Because you now is.
I think 2 minutes will be enough.
Okay.
I have only 1 or 2 slides.
Okay.
So we can define these values alpha and beta for any multi-index finite, and also we can define them for infinite multi-indices. We can define them also for infinite multi-indices, and now we can introduce a representation space. Representation space, we need some Hilbert space. So we do the following. We consider equivalent multi-indices if they have the same tail up to a shift. So if you have, so it means that if you remove some numbers of coordinates from first and some other number of coordinates from second, then they will coincide. So to each, so we consider the set of all equivalent multi-indices and consider as family of vectors which are indexed by this set, and consider the scalar product for them in the following way. And the proposition is that this is a well-defined and positive scalar product on the set of these vectors. So we can consider a Hilbert space with this completion of set of these vectors. And the main theorem is that if we have this space, if we have if you write formulas like this is very common formula which is similar to Fock representation, but the difference is that we have no Fock vector, we have no vector which is killed by all these operators. So this is another class of operators. These operators are all different from the Fock representations. All representations are irreducible. All representations are different if these multi-indices are different. So the only remark that if we have a Kunst-Joplitz algebra, then in fact these vectors, if you consider previous slide, they form an orthonormal basis, and we have such formulas for representation. So that's all. Thank you for your attention.
Okay. Thank you very much for your interesting talk. And so what about possible questions or remarks, comments? We have just 5 minutes for next talk, but let me ask you something. What about some algebraic version of what your construction? Namely, you replace covers by some field with involution or even a ring. So could it be possible to extend your construction in such case?
Sorry, there was some interruption with sound. Could you please?
Okay, I repeat it. So my question is, so you consider algebras offer complex numbers?
Yes.
Okay, but my question is, what about replacing complex numbers by field or even a ring with involution? Is it possible to extend your construction on such algebraic case?
It's an interesting question. I don't know answer now, but it most likely that this can be done, but I don't know.
Okay, so thank you very much. Okay, any other possible questions? So if not, then let's thank once again the speaker.
Thank you very much.
Now we have a 5-minute break. Thank you. Thank you very much.